Hi ladies, this is lesson 8.2 and this is where we're going to apply some of those concepts of area that we looked at in the last lesson. So in this lesson we're going to solve area application problems, and we're going to use problem solving strategies that kind of split up the diagram that you're given into simpler parts that you already have formulas for. So just quick as a review, let's go over the formulas that we already know about area, because we'll use these shapes: rectangle, trapezoids, triangles, kites, and parallelograms. We'll use those shapes in more abstract shapes in order to estimate area. So let's start just by looking at the area of a rectangle. And we define the area of a rectangle as base times height. The trapezoid, we said half of base 1 plus base 2 times height. And then a triangle, we just said half of base times height. And with the height, we looked at the diagonals. So we said half of diagonal 1 times diagonal 2. And our parallelogram was the same as our rectangle, which was just base times height. So now let's use these formulas and look at some of these shapes on your note sheet. And you're going to need a ruler for this, and you're going to measure in centimeters. And we're going to use our ruler and our measurements to estimate the area of each figure. So again, these are not perfect figures. You're going to have to split these up. And so, as an example, looking at the first one, you don't have a formula for this odd shape figure. But if you think about it as 3 separate rectangles, you can find the area of each rectangle and add it together. So rectangle 1, area of rectangle 1, area of rectangle 2, and area of rectangle 3. The area of that whole thing is the sum of those 3 rectangle areas. B kind of looks like a kite. So you'll measure the diagonals of the kite to estimate the area. C looks like a parallelogram. D is kind of a funny shaped figure, but looks like you could have 2 triangles here. So you'll need to measure the height of both of those triangles. We look at E. E looks like it could be a trapezoid. So we'll need the height and the bases. F, it's not quite perfect, but it looks like it might be pretty close, where if you move this little space here to fill in that gap, you would have a triangle and a rectangle. Then H is a little more abstract again. So let's look to see if maybe we can make it a little less abstract. So maybe you see a triangle, maybe you see a rectangle. And then maybe this might be close to maybe closer like this, or like this, parallelogram. odd shapes like this, the best you can do is estimate. And then G, we might have several triangles and a trapezoid. And again, a few more triangles and another trapezoid. So putting down these shapes, however, most makes sense to you, but you're looking for the area. So you're trying to measure the internal region of these polygons. So here are the shapes that I broke up my pieces into, and I'll give the measurements for those. And again, your measurements might vary a little bit just because anytime you're measuring anything by hand, there's going to be a little bit of variance. But in triangle, or in figure A, I've got 3 rectangles. Figure B is a kite. Figure C is a parallelogram. In figure D, I have 2 triangles. Figure E is a trapezoid. Figure F is a triangle and a rectangle. Figure G, I have a triangle and 2 trapezoids in the top half. And I'm not going to measure all of those, I'm just going to multiply that by 2, because this is approximately half of my figure. And then in figure H, I have 1 triangle. So here are my measurements that I used for my polygons. Again, I got 3 rectangles, a kite, C is a parallelogram, D is 2 triangles, F is a triangle and a rectangle, E is a trapezoid, H is a triangle, and G, I'm looking at a triangle and 2 trapezoids, and then I'm going to double it to get the bottom, which is another 2 trapezoids and another triangle. So now with all my measurements, I've broken those into smaller figures, and then I found the area of each of those smaller figures based on what I already knew about formula for area for different polygons. And I've given now my measurement for area for each polygon. So now the next step is to organize those from largest to smallest. So here's my largest polygon, A. So my largest polygon is A with 7.09, approximately 7.09 centimeters. Then my second largest is H. Third largest is G. And fourth largest is E. And then my fifth is D. And all of these are in units squared. So I measured all in centimeters. So my units are centimeters squared. Then sixth is F. Seventh is C. And eighth, for my smallest, is B. So just by looking at these, it might be harder to determine which is the biggest area and which is the smallest area just by looking at them. So that's why it's important to be able to break them into smaller pieces, because you can find the area of those smaller pieces. And then once you have the area, when you have a numeric value, it's much easier to rank than just a figure. So here's where it's gonna, where you're gonna be able to apply these kinds of problems. So in this extra example, Brian wants to know how much paint he needs to buy if he only buys 1 can of paint, and 1 can of paint is gonna cover 500 square feet. Is that gonna be enough given his room? So let's find the area of his room first. We've got 14 feet by 12 feet. And he's got a height of 10 feet. So if you think of the area of his room, if it's 14 feet by 12 feet, okay, that would be his floor area, where this is 14 feet and this is 12 feet. But then he also has a ceiling. So his room really looks it's a three-dimensional. And his ceiling is 10 feet tall. So you want to know how much paint he needs to buy, how many cans of paint he needs to buy in order to cover all of these spaces. So really, if you're thinking about how much space he's covering, he's covering this wall. That's one wall. And then he also has to cover this wall. So he's got two red walls. So this is our red wall right here. So two of these. And then he also has two green walls. So we want to know how much area he has to cover because one can of paint only covers 500 feet squared. So the area of his green walls are 240 square feet total, and the red walls are 280 square feet total. So total, all of his walls, he needs to cover 520 square feet. So he can't just buy one can, he has to buy one can plus something to cover 20 square feet. So he might be able to buy, you know, a half gallon or a quarter gallon, but he definitely has to buy more than one. And this problem is similar. We're looking for the area. So Liam is covering a wall in his attic with wallpaper. How much wallpaper will he need to cover the wall? Well, this is a trapezoid because the floor and the ceiling are going to be parallel. And he knows that from floor to ceiling it's 8 feet. So we're going to use the formula for a trapezoid here, which is base 1, 1/2, base 1 plus base 2 times our height. So in this case, base 1 is 18 feet. So 1/2 of 18 plus 12, and our height is 8. And be careful that you measure height perpendicular. This is our height. That 10 feet and that 16 feet, those are just lengths of sides. That's not our height. That height has to be perpendicular to the base. So continuing on, now we're just using algebra here. So we've got 1/2 of 30 times 8 and 30 times 8 is 240. So 1/2 of 240, which is 120 square feet. So if the roll of wrapping paper comes in 100 square feet, that's not going to be enough for him to cover his wall. So he needs 120 square feet or more in a single roll in order to cover that wall. Anytime you're estimating how many rolls you'll need, you have to round up. You can't round to the nearest roll because it may not be enough. So anytime you're looking for a number of rolls of wallpaper to buy, or how many gallons of paint, if it only comes in gallons, or how many crates of milk, you always have to round up. So whatever the measurement is, when you're estimating like this, you need to round up to the next unit, the next quantity. So please jot down any questions you have, and we will go over them next time I see you in class. Thank you.